Welcome everybody. We're going to begin chapter 5 in this video from your geometry book. We're studying in this section the mid-segment theorem. And in general in chapter 5 we're going to continue to study triangles like you were in chapter 4. But we're going to look at special types of segments that you can form in triangles and the properties that they have. A mid-segment being one of those 4 special types of segments that you could form within a triangle. Alright, so we'll cover the others as we get there. Now there's another idea in this section as well that we'll talk about at another time, but the mid-segment theorem is the big deal here. You will use properties of mid-segments to solve problems involving triangles. That's the goal for this video lesson. Alright, well, first of all, I need to explain to you what a mid-segment of a triangle is. And I am specifying mid-segments for triangles because there are also mid-segments for trapezoids that we're going to learn later on in the year. In fact, we've already talked about them once, but we'll learn them officially later on in the year. Alright, now, whenever we're talking about a mid-segment of a triangle, what we're talking about is a segment created by connecting the midpoints of any 2 sides of any triangle. So, let's put a couple points here, a couple of midpoints. Let's say on segment AB and on segment AC. And whenever I connect those 2 midpoints, the segment that I create is called a mid-segment of the triangle. I'm going to name those 2 points. Let's call them M and N. Alright, now just to emphasize the definition of a mid-segment, whenever you draw a mid-segment, you're connecting the midpoints of 2 sides of a triangle, and so that would mean that segment BM is congruent to segment AM because M is the midpoint of segment BA, and that would mean that segment AN is congruent to segment CN because, well, N is the midpoint of segment AC, right? Alright, now that we've defined what a mid-segment is, let's talk about the mid-segment theorem, which we said is the title of this section, right? We need to always know what properties are there with any new type of segment or angle or whatever that we can find. And there happen to be a couple properties that are very useful that go along with mid-segments of the triangles. Alright, whenever you connect the midpoints of 2 sides of a triangle, the segment that's created, the mid-segment, has 2 properties here. One of those properties is that it's going to be parallel to the side of the triangle that it doesn't intersect. Alright, in this case that's segment BC. Mid-segments are always parallel to the 3rd side of the triangle. And there's also a property regarding the length of the mid-segment compared to the side of the triangle that it's parallel with. It turns out that a mid-segment of a triangle is always half as long as the side of the triangle that it does not intersect. So here, the distance from M to N equals 1/2 the distance from B to C. One of the things that we'll talk about at another time in this section 5.1 is what's called a coordinate proof. And you can prove these 2 properties of mid-segments using a coordinate proof. Alright, so we're going to get to that at another time. But for now, just trust me. Segment MN has to be both parallel to and half the length of the 3rd side of the triangle, BC. So let's see how we can use that. Very simple. I've got a triangle here where I've given you that M, N, and P are midpoints. Alright, so M is the midpoint of segment XY, N is the midpoint of segment YZ, P is the midpoint of segment XZ. And I want us to complete these statements using the fact that those are all midpoints. Alright, well, turns out that always you can draw 3 mid-segments in any triangle, and that's exactly what's happened right here is we've drawn a mid-segment by connecting these 2 midpoints together, these 2 midpoints together, and then the last pair of midpoints together. And what we just learned in the mid-segment theorem is that a mid-segment is always parallel to one side of the triangle. So for instance, segment MP would be parallel to segment YZ, and each mid-segment is half the length of the side of the triangle that is parallel with. So MP is half the length of segment YZ. Now with that in mind, I'd like you to see before I narrate what goes in each of these blanks. Alright? A couple of them, especially down here, are going to take quite a lot of thought. But I think that you can get certainly the part A and part B on your own. Try it out, pause the video of course, and then unpause and I'll give you the explanation. Oh, part A, I inadvertently gave you the answer for already. Segment MP right here has to be half of the side of the triangle over there. Well, half of it, but what I meant to say was parallel to, because that's what we're going to put in the blank. So segment MP has to be parallel to segment YZ. Okay, now it's been a while since we've really used this notation right here, but remember when you see 2 points written without any segment or line symbol above them, that's referring to the distance between those 2 points? So this statement in part B was asking you to relate the distance from X to Y to the distance from P to N. Now XY is one of the sides of the triangle. PN is the mid-segment of the triangle that's parallel to that side. And so that means that PN has to be half the length of XY. Or if we're looking at it from the other perspective, that means that XY is twice the length of PN. Alright, hopefully that makes sense so far. Now this is kind of a cool thing right here. Segment NZ, well, that's this little segment right there. And it happens to be congruent to 2 other segments in this picture necessarily. Alright? And let's explain why. First of all, N is a midpoint of segment YZ. And so that would mean that segment YN would have to be congruent with segment NZ, wouldn't it? Because that's the definition of a midpoint. Alright, segment NZ is congruent to segment YN. That's one of the blanks that's going to go right here. Okay, now together segments YN and NZ make up segment YZ, don't they? And isn't segment MP half of segment YZ? And if each of these segments are also half of YZ, that means MP would be congruent to them as well. So you can think of a mid-segment as being half of the side of the triangle that's parallel to, or you can think of it as being congruent to each of the segments created by the mid-segment. They both basically mean the same thing. Alright, segment MP also congruent to segments YN and NZ. Alright, and finally for this picture, I wanted you to tell me which angle in this picture, angle YMN, has to be congruent to. Now this is a little bit trickier. Alright, YMN is this angle right here. Now how in the world are we going to determine what that's congruent to? Well, we're going to use parallel lines here. And we're going to use, of course, the parallel lines created when you draw a mid-segment. You see how angle YMN is, one of its sides is this mid-segment MN? Alright, let me highlight that. And segment MN is parallel to this side of the triangle, segment XZ. And so the corresponding angles that they would form with a single transversal would have to be congruent to one another, right? And both of those lines happen to be intersected by this transversal XY. That would mean then that angle X is a corresponding angle in regards to parallel lines in a transversal of angle YMN right there. So where we were working a whole lot with alternate interior angles in the chapter 4, well, when the mid-segments are involved, you're going to work a whole lot with corresponding angles of parallel lines. Remember, there's 2 different contexts for that word, corresponding angles. I'm referring to the ones for parallel lines right now. All right, angle X goes there. One more set of pictures for us to work with here, or rather the same picture in different information. All right, again, I'm telling you that MN and P are midpoints of the triangle, but what we're going to do here is we're going to find some distances. I'm asking you to find the distance from X to Z if I know that that distance is equal to 8x minus 6, and that the distance from m to n is equal to 2x plus 3. All right, well, hopefully you realize that if we're going to find the distance from x to z, knowing that that distance is equal to 8x minus 6, we need to solve for x first. And we then need to come up with an equation that's going to solve for x. Well, we have two different distances here that are defined in terms of x. So let's see what the relationship is between segment xz and segment mn. And well, since segment mn is a midpoint, is a mid-segment that's parallel to segment xz, we can write one of two equations here. I prefer to write this one because it doesn't have fractions in it. We can say that xz is twice as long as segment mn, right? Or the distance from x to z is twice the distance from m to n. And if you see that, then all you need to do is some substitution. We'll put 8x minus 6 in place of xz, and then we'll set that equal to 2 times 2x plus 3. Little algebra, and voila, we will have the value of x and then the length xz. All right, well, let's do that algebra. After distributing, you'll have 8x minus 6 equals 4x plus 6. And then when you subtract 4x from both sides and add this 6 to both sides, you get 4x equals 12. So x is going to be equal to 3. Now, of course, the problem didn't tell us to find x. It said find the distance from x to z. X was just a necessary thing to use in order to find this distance. Now we'll go ahead and say then that xz equals 8 times 3 minus 6. That's 24 minus 6, or 18. All right, hopefully that makes some sense to you, right? I want you to try this next one on your own and then have me check the answer. Well, check your answer with me. Go for it. Now, I think you realize this was a variation on the previous problem. I'm telling you to find this distance from m to y this time. And I'm telling you to find that distance if you know that it's 4y plus 1 and that Pn, which is right here, is 6y minus 4. All right, well, actually, I told you that mx is 4y plus 1, and I told you that Pn is 6y minus 4, right? Let me change up colors here. I told you this distance, and I told you this distance right there. Well, how are we going to find my using these two distances right there? Well, these are the three distances that we said would be equal to one another. Segment xm is congruent to segment my, since m is the midpoint of segment my, and segment Pn is congruent to each of those two because it is half of segment xy, just as they are. So what we're going to do then is we're going to find the value of y by making an equation out of these two segments, and that equation is that they're going to be equal to one another. Right? We can say that mx is equal to Pn. And then just do your substitution thing. 4y plus 1 equals 6y minus 4. Add 4 to both sides, subtract 4y from both sides. You get 2y equals 5, so y equals 2.5. And then how do we find the distance from m to y? Well, simple enough. That distance is equal to each of these other distances, and so if we just plug in the value of y that we found either here or here, that will tell us the length of the segment that's written here, as well as then the distance from m to y. Let's do it. I'm just going to use the distance from m to x and say that my equals mx, which is equal to 4y plus 1, which then is equal to 4 times 2.5 plus 1, and that gives you 11. Mid-segments are very, very simple things to use. Hopefully that makes sense to you. We will take a look at some other concepts in section 5.1 within class. Thanks for your attention. See you there.